So here we will study about the behavior of any conductor when it is placed in any electric field. Let's say that you are having two metal plates, A and B, and here you can see that plate A is positively charged and plate B is negatively charged. So this creates a potential difference between the region A and B, and this potential difference will generate an electric field in this direction, E naught. So E naught is our external electric field, external electric field. Now inside this region we are placing a conductor, as you can see here. Right. So we know that in any conductor, the only charge carrier which we see is nothing but electrons. So when these electrons inside this conductor experience this external electric field E naught, so they try to move in opposite direction to this E naught electric field. And what happens is that all the electrons, they get accumulated, or you can say they get drifted towards the uh, positive plate A, and they get accumulated at the surface, okay, which is near to this positive plate A. These are all the electrons which are drifted and positioned themselves in this region, and because of which this region or this face of the conductor, which is near to the plate, negatively charged plate B, this face becomes positively charged, because he is not, this region, it is lacking of electrons, so that is why this region gets positively charged. So as you can see here, a certain oppositely directed electric field is generated due to accumulation of all the electrons on the face which is near to positive plate, and accumulation of all the positive charge on the face which is near to the negatively charged plate B. And this E naught electric field EI, now this is the inside electric field. Now this electric field is generated and is having such value which is completely in magnitude, it is completely equal to this E naught. Okay, so this EI which is having equal magnitude as of E naught, and the direction of EI which is opposite to E naught. So what happens is that it cancels the external electric field, because of which we don't find any net electric field in this region, right? So that is why inside any conductor there is no electric field, because this electric field EI, it is completely equal and opposite to external electric field, which cancels it. Alright, so thus in any conductor, the all the electrons which is present here, they are all in static state. Okay, let's say that if those electrons were having a non-zero electric field instead of zero electric field, let's say that if they are having a non-zero electric field, a net non-zero electric field, then what will happen, that inside the conductor the electron will experience a force, and they will be having a random motion, and because of that random motion in any conductor we will see a certain current, right, which is not possible. So that is why our net electric field inside the conductor is always zero. He cannot have a non-zero electric field. He will always have a zero electric. In our next topic, we will see the properties of conductor when it is placed in an electrostatic field. So here we will be understanding, how a conductor behaves when we place that conductor in an electric field. Okay. So we are going to discuss all 5 points we are seeing here. So our very first point is that when you place a conductor in any electric field, then the inside part of the conductor, there is no electric field. And we have understood this very first point in detail few minutes back. Okay, so we will go directly to our second point, and the second point states that when you place a conductor in any electric field, the field lines which is entering or the conductor or which is leaving the conductor, right? So those field lines is always has to be in perpendicular to the surface, right? So this is our second property which a conductor shows when you place it inside any electric field. So let's just understand what the second point is actually talking about. So let's just consider that that this is my any surface of the conductor, and these field lines which you see here, this field lines always has to be perpendicular to my surface. That means in this case this field line is coming out of this surface of the conductor, right? Another case will be the field lines, if it enters the surface, it will always be again in perpendicular position to the surface of the conductor, right? So all the field lines will always be perpendicular, right? Whether the field lines is entering or leaving, it doesn't matter. It has to be at 90 degree to the surface, right? Now let's just say that instead of having perpendicular position, let's say that you are having an electric field who is not normal to the surface, but instead he is at certain angle inclined to the surface. Then what will happen? This electric field E will have components, obviously. One of the component will be tangential to the surface, and the other component will be normal to the surface, right? So we will have two components. Now what will happen, since we are having a tangential component, a component which is tangent to the surface, now this tangential component of this electric field E will provide certain force to the charges at the surface, and because of that force provided by this component, what will happen, the charges at the surface, they will tend to move, that is they will not remain static, and because of which we will see a certain flow of surface current, right, which is not possible in practical, right? We don't see a conductor who is having a surface current when you place it in an electric field. So that is why the field lines, which we provide to any conductor, the field lines will always be normal to the surface. It cannot be at any other angle apart from 90 degree, right? So this is our very first point. Now, our third point is states that if you consider a conductor and if you provide in certain charge to that conductor, all those charges will exist only at the surface of the conductor, and there won't be any kind of charge inside the conductor, right? So we are going to understand this, how we see charge only at the surface and why not, we see charge somewhere inside the conductor. Okay. So let's just consider that you are having a conductor, okay, and you provide him certain charge, okay, you provide him certain charge Q to this conductor. Okay. So let Q be the excess charge. Let Q be the excess charge given to this conductor. Given to this conductor. Right? Now what we will do, we are going to assume a Gaussian surface inside the conductor. Okay. So this is my Gaussian surface. But you have to assume this Gaussian surface a little bit closer to the surface of the conductor. Okay, so let a Gaussian surface is assumed inside the conductor, but closer to the surface of the conductor. Now we are going to apply Gauss theorem, and we are going to find out whether we see any extra charge inside the conductor or not. Now from first point we have understood that inside the conductor there is no electric field. So applying Gauss theorem. Now Gauss theorem says that whatever number of field lines will be there, or the field lines which is crossing normally through the Gaussian surface, that will be q times, or 1 by absolute naught times the total net charge inside the Gaussian surface, right? So our phi, that will be expressed as something called integration d EDS, right? Multiplication of field with the surface area, and that will be 1 by absolute naught times the total charge inside the Gaussian surface. So Q, we assume that Q is the charge which is confined inside the Gaussian surface. Okay, inside the Gaussian surface. Inside the Gaussian surface. Alright. Now since for any conductor, your electric field, E is the electric field inside the conductor. Now since E is 0, so that means your phi value will also be 0. And since your phi value is 0, so 1 by absolute naught times the Q. Now that value also becomes 0, because of which we see that Q value is 0. That means at the beginning we had assumed that Q is nothing but the charge inside the Gaussian surface. So we have found out that if you consider a Gaussian surface inside the conductor, so for that Gaussian surface you don't have any charge, right? So therefore no charge exists. No charge exists inside the conductor. All charge will exist only at the surface of the conductor. Okay, so this is what our second point says. Now, a very last point, it states that the electric field which will be existing at the surface of any charged conductor, that will always be equal or proportional to the surface charge density. Before going into this, we will understand what is surface charge density, and then we will be discussing what is the relation between the electric field and the surface charge density there. So for this, what we will do, we will be considering conductor. Let's say that you are having this conductor, and let's say that you provide him certain charge. Okay, so let sigma be the charge density. Okay. And when we say charge density, so it is nothing but charge per unit area. Okay, for this conductor. So you have provided him sigma charge density there. Okay. Now, since electric field, now what we will do that we will be considering any surface there. Let's say that you consider a surface. This is any surface over this conductor, and let's say that he is having an area of del S. Okay, he's having an area of del S. Now, since you provide him certain charge, so what will happen? A certain electric field, he will be electric field is going to come out, or it is going to cross or pass through this surface with surface area del S. Let's say that E is that electric field. Okay, so therefore flux through the surface element del S. That flux is nothing but multiplication of electric field and surface area. Alright. Now again we are going to express this flux value in terms of Gauss theorem. Okay. So applying Gauss theorem, we find phi as nothing but q by epsilon naught. Right. And if we express this charge in terms of charge density, remember charge density is nothing but charge per unit area. And when you find your charge value, so it is nothing but multiplication of surface charge density with the area of this surface element, because we are doing this process only for the surface element del S. Right. So we are going to express it something like this, sigma del S. And again from this first equation, we have seen that phi is nothing but multiplication of E del S. So we express it in terms of E del S. And when you cancel out this del S value, so you see that electric field is nothing but sigma by epsilon naught. Alright. So from here we observe that electric field E, which is directly proportional to your surface charge density. So for any conductor which you use, and if you provide him certain charge density, the electric field generated by that conductor will be proportional to the surface charge density. So the more the value of surface charge density you provide, the more stronger the electric field he will generate. Okay. Now vectorially, this electric field E, it will be expressed as something like this, sigma by epsilon naught n cap. Now n cap is the direction in radially outward. It's providing a radially outward direction. Alright. So that is why our fifth point, it says that the electric field of any charged conductor, it will always be proportional to your surface charge density. So these are all the 5 properties which the conductor shows, or how it behaves when you place it in any electric field. Okay, thank you then.